Okay, it's time for starting the next session. So I'd like to start with the brief introduction of this session. So thank you very much for coming back. I'm Yukie Nagai, working at the University of Tokyo. And this session will have 1.5 hours in total. And we will have the 5 short talks first, and then the panel discussion for 40 minutes. And here is the, you can see all the speakers for this session. I hope the other speakers are already online here. And I just give you the brief overview of the topics of these sessions. These are the keywords of each speaker's research. I'm working on the cognitive developmental robotics and computational neurosciences, and the others are mainly working on like the soft robotics, smart materials, like the artificial muscle and the self-assembly machines and so on. And I actually realized that by looking at the research, the activities, only I'm mainly working on the computational intelligence. Of course, I try to integrate the embodiment in the computational intelligence, but the other speakers are more strongly focusing on the embodiment intelligence. So during the discussion, I'd like to highlight the differences and also some the difficulties in bridging the gap between the computational intelligence and the embodied intelligence. And I'd like to receive their opinions of the other speakers, how the embodied intelligence can be utilized for further facilitating their computational intelligence and vice versa. So please let me give you the first overview of my research on activities. So the title is my talk is the Embodied Predictive Processing for Cognitive Development. My research group had been there developing the computational neural networks model for robots to acquire their cognitive abilities. For example, the human babies acquire their abilities to estimate the emotional state of others and also imitate their emotional state through the social interactions. The research question is, what neural mechanisms enable human babies and also the robots to acquire this kind of the cognitive development? And we have been focusing on the theory from the neurosciences, which is called the predictive processing of the brain. The key idea here is that our brain works as a predictive machine. When we perceive the world or act on the environment, our brain does not simply utilize an incoming sensory signal, like a vision or audio signal, or also the proprioceptive signals and the interoceptive signals as well. But then our brain utilizes our top-down knowledges or the previous experiences to make a prediction about the world. And basically, the brain tries to minimize the prediction error, which is the discrepancy between the top-down prediction and the bottom-up sensation. And based on the theory, we have been extended the ideas to the cognitive development, so that, for example, to investigate how the embodiment will impact on the development of our cognitive abilities, and also their sensory motor learning based on the embodiment will facilitate their acquisition of their various types of the intelligences. And I'd like to give you one example which shows the impact of the embodiment on the intelligence, the emergence of the intelligence. In this experiment, we have designed a computational neural network model, which can learn to manipulate an object. And here, the key idea is that the camera image as a visual input and the joint angle as a proprioceptive input are integrated into the modality representations here. And then the network basically tries to minimize the prediction error. It reconstructs the original input image, that's a multimodal signals, and then the network tries to minimize the gap between the discrepancy between the predicted signal through the network and the sensory input. Their strategy itself is very simple, but the interesting point is that after learning this multimodal, the integrations, the network can be also utilized for estimating or predicting their other robot, their behaviors. For example, when the self-robot, which learned to generate the motor experiences, can also estimate the goal or intention of the other robot, where the challenge is that the other robot, so the observation of the other robot that provide the self-robot the different perspectives, and also there is no access to the joint angle of the other robot. But still, the self-robot can make predictions about their visual perception and also the corresponding proprioceptive signals. Here's the result. Here, this is an observation of the other robot. The other robot is always located on a different side of the table. So the perspective of the visual scene is quite different from its own motor experiences. But nevertheless, this network model, which have trained by integrating the two modality signal, the visual input and the proprioceptive signals, can make predictions that are like an adaptive predictions of their observations. For example, in this case, the other robot is pulling the object toward the body. Then their predicted their behaviors is also achieving the same goal, which is the pull behaviors of the object. So if you look at only at their orientation or the direction of the object movement, you realize that their direction is quite different between the observed behavior and the generated behaviors. And interestingly, depending on their observational signal, the robot can adaptively switch their estimation of the goal. When the observation of the other robot is only limited to the hand, then their output, the prediction of the other robot behaviors also change towards their pushing behaviors. Because there is no clue about the position of the other robot body, then the self-robot can utilize only the hand movement to make predictions of the other robot goal. So in that case, there you can see that this predicted behaviors is quite different from the original predicted behavior, which was the pulling. And here it is the pushing of the object. And interestingly, if we introduce again the part of the body, then the robot estimation of their other robot behaviors again change toward the pulling behaviors. So this really showing that how the embodiment can really help the robot to adaptively switch their intention reading in this interaction scenarios. And then we can also more strongly verify the impact of their embodiment, the sensory motor learning. So in the left side condition, we trained the network model through the March model sensory motor experiences. The visual input was integrated with the proprioceptive signal. In this case, the network could successfully make a prediction of the observation. But if we train the network model using only the visual input, which is like corresponding to the learning through observation, in this case, the predictions of the network becomes very inaccurate. You can see that the output of the visual, the predictions get lowered, which is corresponding to the low accuracy of the predictions. So we can show from this experiment that the embodied sensory motor experiences is crucial for acquiring more accurate sensory motor mapping and thus the prediction abilities. This is an additional analysis to visualize how the March model signals are integrated into the neural network model. You can see that the visual and the proprioceptive signals are largely merged into the single the spaces, and then at the end of the learning, these two modality signals are completely showing the completely overlapping representation, which is the basis of the March model, the prediction ability. So here, this is the summary of my part. So my key interest is to investigate how the brain, their mechanism would support their cognitive development. And then there not only a computational part of their in the brain, but also their experiences through their embodiment really helped the development of the prediction ability that we could find in our own experiment. Just one example of our experiment, but I hope that you could get the idea that the March model integration based on the sensory motor learning and also the embodiment plays an important role for acquiring this prediction ability in the brain. So then now it's time for introducing the next speaker. So we have Fu-chan Chao, the second speaker. So if you're here, yeah, great.
Hi.
So I'd like
Hi,
to
Yukie.
stop
Nice
my
to see
sharing
you.
the screen. And for the audiences, if you have any questions for the speakers, please write down in the chat or the Q&A so that we can pick the questions at the end of our sessions. Okay, Fu-chan, if you are ready, please start your presentation.
Hi, Yukie. Can you see my slide?
Yes, we can see.